Okay, hello everyone. Welcome to the Jagiellonian Theoretical Computer Science Seminar. Today we have James Davies. James is a PhD student at Waterloo, at the University of Waterloo. He is well known for his work on chi-boundedness. Just to name a few results, he proved chi-boundedness of proper classes of graphs which are closed under taking vertex minors or pivot minors, and something closest to my interests is polynomial chi-boundedness of circle graphs, where he has a first joint paper with Rose McCarthy showing a quadratic upper bound, and then he has a paper showing an omega log omega upper bound. All great results, and today he will be speaking about Ringel's circle problem, which is also kind of coloring or chi-boundedness problem. Yes, the floor is yours.
Thank you. So yeah, Ringel circle problem, and this is all joint work with Kaya Keller, Linda Kleist, Shahar Smorodinsky, and Bartos, who gave me the nice introduction. Okay. This doesn't seem to work. Wait.
Hello? Yeah.
Yeah, okay, now it's working. Okay, thank you. Okay, so the kind of graphs we're going to look at, tangency graphs. So the actual geometric objects we're going to be looking at is just circles in a plane. And what we're interested in is tangencies. So we can define a tangency graph from a set of circles in a plane. So here we're going to have vertices corresponding to circles, and two vertices are adjacent if their corresponding circles are tangent. So this collection of circles gives this tangency graph.
James, maybe you could show with your hand, because the pointer is not visible remotely.
Okay. So these circles give you this tangency graph, but it's often going to be more convenient just to look directly at the circles. So we're going to be interested in coloring. So if we want adjacent vertices to be different colors, this is just the same as tangent circles being different colors. So Jackson and Ringel gave a nice exposition of coloring problems you can ask about for tangency graphs of circles. The first one, which is like a warm-up and quite a nice exercise, is what's the maximum chromatic number of penny graphs. So here, penny graphs are tangency graphs of circles where our circles are all going to be of the same fixed diameter, like the same size as every penny, diameter 1, say. And we also require that our pennies are non-overlapping. So this configuration of pennies so that you need at least 4 colors to cover them, and it can be shown that 4's enough. So these are obviously planar graphs, but it's easier than that. You can show this is 3D degenerate if you just take some outermost circle. That's a nice warm-up one. Another harder one is coin graph. So maximum chromatic number of a coin graph. So it's just like a penny graph problem, only now coins. So we can take our circles to be of whatever diameter or size we want. And we just require that they're non-overlapping still. So again, you need at least 4 colors. And you can apply the 4-color theorem to say that 4 colors are enough. Actually, really surprising theorem, particularly because of how old it is, I think, is that actually this is equivalent to the 4-color theorem. So every planar graph is a coin graph. So this problem was actually just the same as asking for a maximum chromatic number of a planar graph. Okay, a third circle problem. What if we now allow overlapping circles? But we'll restrict back to pennies. So our circles are diameter 1, but they're allowed to overlap now. And we can have something like this. And then the overlapping penny problem is how many colors are needed to color these graphs. So actually, this is equivalent to a very well-known problem of coloring the plane. So this is equivalent to a problem of you want to color the plane so that no 2 points at unit distance are the same color. And the reason this is equivalent is because 2 circles of diameter 1 are tangent exactly when their centers are unit distance apart. So this is equivalent to this problem. For upper bound, we have this 7 coloring hexagonal tiling. And there's this recent breakthrough of a 5 chromatic unit distance graph. So the answer for this one's between 5 and 7. Okay. So now on to Ringel's axial circle problem. So this setting will generalize these all these previous ones. So now we're allowed circles of any size, any diameter, and they're allowed to overlap. We're going to have one restriction on our collections of circles, and that we call a constellation. But I'll get to what that slightly technical restriction is in a bit. So Ringel's circle problem asks what the maximum chromatic number of these constellations, call them, the circles. So for example, this configuration is 5 colors. So what's this weird constellation condition? So what it's saying is that we have no 3 circles all tangent at a point. Why would you ask this? Well, if you didn't have a requirement like this, you could have some very silly example like this, earring looking thing with a ton of circles all interiorly tangent at a point. This is like a clique, they must all be colored differently. So a restriction like this is important to make the problem interesting. And you know, this is quite an old problem. So if chi-boundedness was already a notion back then perhaps you would have phrased it in terms of a chi-boundary problem, where you forbid the size of the clique rather than this constellation. Okay, so what's known for this problem? Well, for lower bound, this 5 chromatic example is actually the best out of known. And really the only development on this lower bound until recently was this 5 chromatic unit distance graph. So it's another 5 chromatic example where the circles are more restricted. So the upper bound, something that distinguishes this problem from the other 3 circle problems is that no finite upper bound for the number of colors you need to use graphs is known. So actually the main component of Ringel's circle problem was essentially asking if a finite number of colors is enough or not. So our main result is an answer to this question, which is no. Actually, you can find constellations that require arbitrarily many colors. And actually, we can do quite a bit more than this. So we can further make it so that these constellations have arbitrarily large girth, as well as chromatic number. So I think this is quite nice, partly because it kind of removes this weird technical constellation condition of no free tangent at a point, because by having girth at least 4 with forbidding triangles, and you automatically get rid of that. So we can just talk about general collections of circles. Okay, so I want to spend most of the talk giving some idea of proof of this. So I'll mostly just focus on the case where we don't worry about girth, just to keep things a bit simpler. So what I want to do towards this next is introduce the main tool we use for proving this. So what I introduce, it won't be exactly as powerful as we need, but we'll go with that for a while and see what goes wrong later. Okay. So the main tool will be Gallows Theorem. So for this, I need to define a homothetic map and homothetic copies first. So a homothetic map between d-dimensional spaces is just a map you can make from two parts. You have a uniform scaling factor and a translation. And if you can get from one set to another by a homothetic map, then it's a homothetic copy. So as an example, with this purple star, this blue star will be a homothetic copy. We get from a uniform scaling and translation. But this red star is not a homothetic copy because our scaling is not uniform. We've only scaled in the y-axis and not the x. So it's not a homothetic copy. And another one that's not homothetic is this star because we've done a rotation and that's not allowed. So we just have this. We have uniform scaling and translation. And then what Gallows Theorem says is if you finitely color the points in d-dimensional space and you pick any finite set of points t within this d-dimensional space, then you can always find some homothetic copy of t, which is monochromatic. So from your chosen t, you can always do a scaling and do a uniform scaling and a translation to get to a monochromatic set. So as an example of how this works, well, here's what's happened when I've tried to color in all the plane. The mess. But let's say we want to find the corners of a square inside here. So if we enlarge corners of a square, still as corners of the square. Then what this theorem says is that somewhere in here, we'll be able to find monochromatic corners of a square. So we can find it here, for example, these 4 green points of a square, like so. Taking this out so you can see it better, it looks like this. But you can always find this. And to compare Gallows Theorem to something that's probably better known is van der Waals theorem. So van der Waals theorem is the one that says that if you finitely color the integers, then you can find arbitrarily long arithmetic progressions. And Gallows Theorem is basically a generalization because if we looked on a real line, say, and we picked 3 points evenly spread apart, then homothetic copies of this is just like a 3-term arithmetic progression. The Gallows Theorem generalizes van der Waals, and actually one way to prove Gallows Theorem is by repeatedly applying van der Waals. Okay, so I want to rephrase Gallows Theorem slightly just to make it more finite and discrete, and that'll just be better for applying. So if we have sets t and x in d-dimensional space, then we can actually define a hypergraph with vertex set x. So this hypergraph will have hyperedges being homothetic copies of t. And now your problem of coloring x so that there's no homothetic copy of t is just the same as coloring your hypergraph so that there's no monochromatic hyperedge. And then that's our 3-state Gallows theorem that's saying that if we pick a finite set of points t in our d-dimensional space, and we fix some number of colors k, then we can always find a larger finite set x so that this hypergraph has chromatic number at least t. Or in other words, no matter how you color this finite set of x points, we can always find a monochromatic homothetic copy of t. So this is slightly more useful, mostly just because we get this finite set x, which we can do things with. And the main idea for construction for Ringel's circle problem is to combine the use of Gallows theorem with Tuck's classical construction of triangle free graphs of large quadratic number. So if you don't know it or can't remember what Tuck's construction is, then you don't have to worry about that, because I'm going to go through how we do this construction of Gallows theorem anyway. But if you are familiar with it, then essentially the modification we're doing is just a step in Tuck's construction. We're using pigeonhole principle. And instead of using pigeonhole, we're going to be using Gallows theorem instead. So this idea works for triangle free graphs. If we wanted high girth, like in the result we have, then we actually need to do more. So we need high girth or sparse version of Gallows theorem, which is what this is. So you don't need to worry too much about exactly why it is. Just essentially, if we want these high girth results, we just use this sparse version of Gallows instead, and we maybe just have to be slightly more careful, but it's similar. Okay, so next I'll just show a couple of results, a couple of previous results from this idea of combining Gallows theorem with modifying Tuck's construction. So the first is on box intersection graph. So in this setting, we're looking at boxes in free space, and we'll be looking at whether or not they intersect. So boxes correspond to vertices, and two vertices are adjacent if the corresponding boxes intersect. And then for boxes, we have this classical result of Berling that does triangle free box intersection graphs with arbitrarily large chromatic number. And this is something you can extend using this Gallows theorem Tuck construction technique to actually also get large girth. So in some way, I find this interesting because at least to me, it feels like a more natural setting for Berling graphs now is string graphs rather than their original application of boxes. One more result of this kind is that you can also get this large girth, large chromatic number result for intersections of lines in free space. Similar ideas. Okay, back to Ringel's circle problem. So I'm actually going to start off by showing a proof that is a very severe mistake. So there'll be an issue here, and if you would like, you can point out what the issue is if you spot it early, and I'll just hope that is the issue I have in mind. So, okay, what this first attempt is going to be. So, say we've already got our K-chromatic constellation. These will be these red circles. The idea is that we want to somehow apply Gallows theorem, add in additional circles, add in lots of these K-chromatic constellation gadgets in such a way that we get a new bigger constellation which will bump the chromatic number up by 1 to K+1. So first, starting with this K-chromatic constellation, we need to work towards how we're actually going to apply Gallows theorem. So what we'll do is we'll start by adding this vertical purple line. This is just a reference point. It's not actually any new object. And we'll just make this to the left of our red gadget. And now for each circle in our red gadget, we're going to look at its bottommost point and add a infinite horizontal line. So this will be tangent to our circle and go along and intersect that purple line. So I want you to think of these infinite horizontal lines as just like circles. They will be circles in our constructions later on, but they have the same tangency properties, and we'll sort out the fact that they're not actually circles later. Okay, so this intersects our purple reference line, and at each intersection point, we're just going to put a point down to mark this. And this is where we want to now apply Gallows theorem. So actually, we're going to be applying Gallows theorem in one dimension, and we're just going to be applying it along this purple line. And the set T we choose is going to be these points of intersection with these horizontal lines, these ones. So from Gallows theorem, this is going to give us a bigger set of points on this purple line, so that in any K coloring, we're going to get some monochromatic homothetic copy of these three red points. And this is what we'll use later, so we bump the chromatic number up. But first we need to add more circles in. So the next thing we do is for each of these points we've gotten out of Gallows theorem, on the purple line, we want to add in one of these infinite circles, one of these horizontal lines. We do that like so. So this is going to be like our Gallows set of circles that we get directly from Gallows theorem. And now we want to look at homothetic copies of what we started with here. So say we're now looking at this blue homothetic copy, so we had to scale it down. So we had to enlarge it and translate downwards. Then looking at this homothetic copy, we look at these horizontal lines from it. And this is where we want to add another copy of our original K-chromatic constellation, but this will be a homothetic copy. So we'll scale it up and translate it appropriately. So by copying the scaling factor needed for this, we get the correct scaling, and then we can just translate it along these blue lines. And we just translate it along to try and separate it so it doesn't interfere with what's happening with our previous gadgets. And we're just placing this blue K-chromatic gadget to lie just on top of our blue Gallows circles. And this is something we do for every single homothetic copy of our red ones. Okay, so we can do, we can add these in safely. So now I just want to show that we've actually bumped up the chromatic number. So let's go back to looking at our horizontal Gallows lines, and we consider a K coloring of them. So let's say, then what Gallows theorem says from these points X are outputted is that in any K coloring, we can find a homothetic copy of our original red vertices that are all the same color. So here, for instance, we find these three green ones, all the same color. So a homothetic copy, so we put some gadget on top of it. So now every circle in our gadget is tangent to one of these green lines. We know our gadget's got chromatic number K, so we need K colors to color it. We have K colors available, but we've lost this green color for every circle. So we actually only have K minus 1 colors, so that's not enough. So we bump the chromatic number up by 1. Okay, so this construction almost works in a sense. The chromatic number stuff works, and this picture looks fine, except for you might rightfully be concerned about all these horizontal lines that aren't actually circles yet. So what we would do now to get rid of these horizontal lines and make them into circles is to apply its transformation called an inversion. So this will turn circles into circles, and we can consider these infinite lines as like generalized circles that just go to infinity, and these can be transformed into regular circles this way. And we would end up with something like this. And this is where the problem lies. Essentially, these infinite horizontal lines, considering them as circles, you could consider that they're actually all tangent to each other at some point at infinity. So this is what goes wrong with this attempt. But this is also somewhat silly in some sense, right? Like, the problem is we're getting these internal tangencies, and that's a big leak. That's why we're forbidding this. But we're not actually using the fact that these things are adjacent or should receive different colors. So if somehow you could like modify this here to break the tangencies, it would be done. But this thing's too rigid to do something like that, so it doesn't work. But this proof can still give you some things as a kind of consolation prize. So we get this result for every theta except for 0. So if instead of defining adjacency between tangent circles, so you can imagine circles intersecting at an angle of 0, you pick some other angle theta, then this proof will work. So if we define adjacencies by when two circles are intersect at an angle theta, for example, if you want to do orthogonal circles, then this will work because inversion preserves angles, and the only intersecting angles we're doing by accident is all of these ones at 0 of these lines going to infinity. So in some sense, so this proof doesn't work for 0, which is what Ringel's circle polynomials actually was. But we kind of come close in some sense already from this. And again, you can do large curves. Okay. So we got some stuff out of this, but ultimately the attempt didn't work. But we can try something like this again. And we just want to rethink about how we apply Gallows theorem. And we want to do this in a way that we're not just getting these massive internal tangencies. So this time for a second attempt, and by the way, there will be a problem in this one as well, just not so major. And we'll be able to fix it at the end with a more restricted Gallows theorem, which I'll get to. So this time we're going to apply Gallows theorem in 3 dimensions rather than 1. So this is slightly odd at first because, you know, we're doing a coloring problem in a plane, so 3 might seem a bit strange. But you can represent circles in 3 coordinates in free space, but then this becomes more natural. So given a circle, we can represent it as a point in free space, coordinates x, y, r, where x, y is the center of the circle and r is its radius. So we can go between our constellation of circles, this k-chromatic one we want to bump up, and points in free space. So close to what we would want to do is directly apply Gallows theorem on these points in free space. But this will again run into problems where there's really unavoidable internal tangencies. So we want to apply on a set slightly different to this x, y, r we get from our circles. So actually the only alteration we'll do is that we're instead going to apply it on this set. So we're essentially taking a reflection in the xy plane. So we're taking the negative of the radius list for our set T that we'll apply Gallows theorem to. And in this application of Gallows theorem, I actually want, for set x I get out of Gallows theorem, I want to almost immediately already be getting circles out of that. But something silly here is, well, what does it mean for a circle to have negative radius? We maybe want to get rid of something like that happening. So all we'll do once we've got this x out of Gallows theorem is translate along the z-axis, translate a whole set way up. And what this means for our circles is we're just increasing the radius. So we make them all positive and we can make them all large. And we can do this so we get some kind of set like this out of Gallows theorem. So for convenience, we make all our circles radius large enough that all the centers are contained in all the circles. And by making these radiuses big, we can also avoid external tangencies. So that takes care of our like Gallows circles. What we need to consider next is how to add on these k-chromatic constellation gadgets. So if we look at the homothetic copies we would have get from our original constellation, we just had these x, y, r's instead of x, y minus r's, then they'll look something like this. So this isn't something you can attach onto the circle straight away. That we need to move them somehow. But actually, this is where the minus r comes in really handy, because in some sense, this negative factor we're getting out of Gallows theorem almost, and those homothetic copies are kind of exactly counteracting the positive factors we're getting from taking homothetic copies of our axial circles. So what this will mean is if we're looking at one gadget we want to attach, say it would have originally looked like this. We're now going to be able to translate it all some fixed distance in such a way that these circles are now going to lie tangent to these bigger circles with each of these centers. So this is how these r's and minus r's. You can just take my word for it that they cancel out. And this lets them all lie exactly on these circles. And one very important thing here is that actually the angle we translated out at wasn't important, only the distance was. So we could have picked any of these. We could have placed our gadget here or here, say. So this is a good thing to have because it gives us flexibility when adding our gadgets, and that means we can place our gadgets so that they don't interfere with each other in any unwanted ways. Okay, so let's look at one more of our homothetic k-chromatic constellation gadgets we want to add. May have looked like something like this. We look at these larger circles with these centers. And we can just translate it out somewhere like this. Okay, so this bit all works fine. And to show that we bumped up the chromatic number after we do this for all homothetic copies, this is essentially the same argument as before. So we just go back and look at the circles in Gallows theorem. We consider k-coloring. We know from Gallows theorem this is going to contain a monochromatic set from a homothetic copy. These ones say corresponds to these, and somewhere here we placed a gadget. And now this is the same thing. These circles give you a k-chromatic tendency graph, but they each have one less color available, but they're only a k-1 colors despite needing k. So we bump up the chromatic number to k+1 again. Okay. So this construction almost looks like it works, but there's something there's one step where we really couldn't guarantee that things were going to go our way. And this was almost the first step, actually, when we first applied Gallows Theorem. So this gave us these circles here, and we did this translation to make the radiuses bigger. This had some nice things, like we had this neat thing where we could make all the centers inside, and we could get rid of internal tangencies. But something increasing the radius won't do is get rid of external tangencies. Sorry, get rid of internal tangencies if you're unlucky to get an internal tangency. We'll get rid of external ones, but not internal. So if you're lucky and get an internal one, you can't get rid of it. So for instance, if our x we got from Gallows Theorem gave us something that looked like this, we could try and enlarge the radius, but it's just translating, adding a constant factor on the radius. So we're just moving this point where you're internal tangent further away. So this is really where this attempt goes wrong. But also, this doesn't seem like much a disaster as the first one, right? We just need to figure out a way to get these set x out of Gallows Theorem, which doesn't create this problem. So one natural thing to do here is actually just throw this into our inductive argument. So the idea is we just throw this in and say that in our constellation that we're building a pi chromatic number, we have no two internally tangent circles. And one reason this is important to throw into the argument is because if we have two internally tangent circles and we apply any reasonable version of Gallows Theorem to these things in this way, then we're always going to generate lots and lots of internally tangent circles from the set x in that last construction. So we really do need this in our inductive argument. This actually introduces one small issue that wasn't present in the construction before. And this is when we're adding on our k-chromatic constellation gadgets. So say we had two concentric Gallows circles, and we wanted to add on this red circle of one of the k-chromatic gadgets. Then here's the problem we could have. No matter what angle we choose to translate this out of, the line in the circle, we might always then be internally tangent to this outer concentric circle. And this is bad because any angle won't get rid of this. The thing of being able to pick any angle was really strong, but this is kind of a one situation where you won't be able to pick an angle to get rid of these problems, exactly if you have concentric circles. So something natural, and we have another problem is throw this into the inductive argument as well. So now we're going to say we're constructing our circles. We've tangent graph as large chromatic number, and no two are concentric and no two are eternally tangent. This is the theorem we want to argue inductively on now. Of course, the crucial missing ingredient is how do we maintain this property when we apply Gallows Theorem? This can be maintained from each gadget we add on, so we have a lot of freedom choosing the angles, but the roadblock is when we apply Gallows Theorem, we want to maintain this. So let's have a look at what it means to be, for two circles to be concentric or internally tangent. So these are very simple properties, right? We just look like this, a concentric, this one internally tangent. And viewing our circles as points in three-dimensional space, we can actually get a very simple polynomial condition for being concentric or internally tangent. So two circles are concentric if and only if it's a concentric polynomial. So in 6 variables or in 2 3-dimensional variables is equal to 0. So all this is doing is looking at the xy, their centers, and that's all concentric means, right? If the centers are the same. So this is assessing the distance between the centers. So they're concentric only when this polynomial is equal to 0 for these 2 points, the points of the circles. And you can do the same kind of thing for internally tangent. Here, these 2 bits are missing the distance between the centers essentially, and then this r minus r2 bit squared. It's just for the difference in the radius. So again, we're internally tangent only when inputting into the polynomial for a 0 point. So we just need to avoid 0 points of the polynomial. And this will motivate our restricted Gallows theorem that we need. So first, one definition before I can state it. So a family of polynomials in 2D variables, lots of D variables. We say respect a set X in D-dimensional space if for any polynomial in our family and any pair of distinct points, P and Q from X, we have that f of PQ is not 0. So this captures what we need, right? If our P and Q are both representing circles, we need these to be non-zero to not be concentric and non-zero to not be internally tangent if we pick the appropriate polynomials. So here's our polynomially restricted Gallows theorem. So a lot like Gallows theorem, we have this finite set T in D-dimensional space. We have this number of colors K. The main difference is we now have this family polynomial in 2D variables, and this is a family that respects T. And then the theorem says, as before, we can find this finite set X, so that in any K coloring, we find a homothetic copy of T. But more than that, we can guarantee that our family of polynomials F also respects X. So what that means by respecting it is, again, when we take pairs of points, it's a non-zero. So we maintain being not concentric or not internally tangent. So there's a slight subtlety here. We weren't applying Gallows theorem directly to our circles X, Y, R, right? We're applying it to this X, Y minus R. But and we're also doing this translation along the Z or R axis. But actually, this doesn't change this condition. We have this R1 minus R2. For increasing R, they're going to cancel out. We take the negatives. This is the same thing. It's just a difference. So that's all fine. So basically, once we have this restricted Gallows theorem, by using that instead of a regular Gallows theorem, we know that these Gallows circles we get from our construction earlier, none of them will be internally tangent circles, and none of them will be concentric. And that enables the construction to work. So all we need to finish a proof of Ringel's, all we need to finish this solution to Ringel's circle problem is to prove this restricted Gallows theorem. So to prove this, we need the Hale-Stewart theorem. So if you're not too familiar with this, or it's your first time seeing it, then might be going through it a bit quickly, but hopefully you can get something out of this proof. I think there's some nice ideas even if you don't see everything that's happening. So first, to describe what Waals theorem is. So one way to state it is if you have a finite set T, then the object we're going to look at is large hypercubes on T. So if we have some n-dimensional hypercube on the set T, this is the object it will be coloring, and the sub-object inside we care about is combinatorial lines. So a combinatorial line is going to consist of a subset of our n-dimensional hypercube, which will be made from some non-empty index set. So indices for the coordinates of a hypercube. And then our combinatorial line is going to consist of some fixed points or some fixed coordinates. So the coordinates not in our index set, we're just going to fix points for. And then for the coordinates of the index set, we're going to set the values in each of these coordinates the same. But it can be any one of these values in T. So each element of T gives you a different element of your combinatorial line. You're just moving this index set of them all being equal. Okay, so what Waals theorem says is that for any finite set T and any number K, there's an n so that the n-dimensional hypercube on T, no matter how you K color it, you always have a combinatorial line. And we need to use this to prove our polynomially restricted Gallows theorem. But first of all, as a warm-up, I'll go through how to prove it, how to prove this regular Gallows theorem. So this isn't too bad. First natural step is we've got our T from Gallows theorem, and we've got the K. So we just let n be what we would get from Waals theorem, the dimension of a hypercube for T and K.
So this can't be the original proof.
Sorry?
This can't be the original proof. Because
No. Yeah, so Waals theorem generalizes Gallows a lot. Yeah. But I like this proof of it a lot. Okay. So the next step, once we've fixed this n from Waals theorem, is to now explicitly construct a set X. So the way we construct this is just for each point in our n-dimensional hypercube on T, coordinates T1 through Tn. We're just going to include the point T1 plus all the way through plus Tn. So this might not be one-to-one, but for now that doesn't matter. And again, X is a subset of RD. Now, if we had a K coloring of our set X, then going backwards, this would give a K coloring of our hypercube. This means from Waals theorem, we can find a combinatorial line in the hypercube that's the same color. So all that remains to complete the proof is check that if we go back from this combinatorial line in the hypercube back to our set X, that this is a homothetic copy of T. And if you just do the calculation of what this set is, you get is this. So the number of elements of your index set of I times by the set T. So this is our uniform scaling factor for the homothetic copy. And then we just have plus this stuff. This is passing the parts from the non-index coordinates. That's our scaling factor. And this gives a monochromatic homothetic copy. And this proves Gallows theorem. So the idea for our polynomially restrict Gallows theorem is very similar to this. A key difference here is how we define the set X. So here for defining X, we just had 1t1 plus 1t2, so on plus 1tn. For the most part, picking one here was pretty arbitrary. So the main idea is, instead of just fixing these as one, for each of these ti, we're going to put in a real variable, lambda I. So instead, we're going to have lambda 1 t1 plus all the way through lambda n tn. And we'll figure out what these lambdas 1 through lambda n will have to be later. But to go through what's actually happening here. So our polynomially restricted Gallows we want to prove. We start the same way. We fix n as in Waals Theorem for our t and k. And now, as I was just saying, our aim is to be able to pick lambda 1 to lambda n, these n real variables, so that our chosen family of polynomials respects the x we get here. When now our x is lambda 1 t1 plus lambda n tn. So before, we're essentially just taking all the lambdas equal to 1. Now we're allowing them to be any real, and we need to figure out how to pick them later. So one slight technicality, you don't really have to worry too much about this, is we want to add this polynomial to f, to our family of polynomials f. And all this is like a difference polynomial. So this is equal to 0 for 2 points, exactly when they're the same point. So this is clearly these polynomials respect our set T, because we have this condition that we're looking at distinct points anyway, so that's going to be non-zero. So if we so disrespect our set X we get out, then that just means they're distinct, and this will then mean that going back and forth between X and a hypercube is bijective. So you don't have to worry too much about this. Slight technicality. But once you have this property, we again have the same thing that combinatorial lines in a hypercube for them to hypothetical copies. This is why we had this technicality, because if we didn't have this technicality of it being bijective and stuff being distinct, we could end up with something silly where a combinatorial line corresponded to a homothetic copy with a scaling factor of 0, which isn't what we want. Okay. So with this, all the coloring stuff goes through. We do the same thing of going back and forth from X to a hypercube, find that monochromatic combinatorial line, the monochromatic homothetic set. So the part that remains is actually showing that our family of polynomials respects the X we're going to get. So to do this, we're going to consider these other polynomials. So for every polynomial in our family, and these two should be distinct, every two distinct points P and Q of our hypercube, we're going to consider this polynomial FPQ, and this is going to be in our variable called lambda 1 to lambda n. And what this polynomial is equal to is this chosen polynomial f of these two things. So each of these is just going to be a d-dimensional point. This sum of lambda I pi, exactly what we're doing for the set X. And then yeah, this would just end up being 2 points in that's just 2 points on a D space. This is our respect thing, which we'll have to sort out. So the next bit is that a family of polynomials will respect f if we can choose lambda 1 to lambda n so that each of these FPQs is not equal to 0. Okay. Yeah, we're looking at pairs of distinct points. These correspond to points in X. These are polynomials. So that's each of these FPQs we're looking at. So let's just focus on one of these FPQs. So we can say that the 0 set of 1 has measure 0. And this is just because it's a polynomial and it's a non-zero polynomial. It's just something you get if you have a non-zero polynomial, like a polynomial that's not identically equal to 0. So all we need for the 0 set to have measure 0 is so that it's not identically 0. But this is easy to say that it's not identically 0 by our inductive argument, because P and Q are distinct points in a hypercube. So in some coordinate, the distinct points are T. In this coordinate, I say, we take our lambda equal to 1, and we take all the other lambdas equal to 0, as in here. And now what we get from the summation 2 is just our F of Pi, Qi, Pi and Qi just points in T. And we know by the induction that this is non-zero, because we know that our family F, so this polynomial F in particular, respects the set T. So each of these FPQs is not identically 0. The 0 set is measure 0. And then we just take the union of these 0 sets. These all are measure 0, so the union is measure 0. And because union of 0 sets is measure 0, we know we can actually take some lambda 1 through lambda n. So that each of these FPQs of lambda 1 through lambda n is not 0 at that point. And this is exactly what we needed for our family F to respect the X we get out of our Gallows argument. So by finding this lambda 1 through lambda n outside our 0 sets, we're done. F respects X. Okay. To finish off, I'll just mention some very open-ended questions. So we got this restricted Gallows theorem, and you can actually strengthen this a couple of ways. So you can do this high girth version again. This is what we need for our high girth results. And really the only thing that was important about this family of polynomials is that 0 sets had measure 0. So other things where that's true, this also holds, so analytic functions. But what else can you do with this? So in some sense, it seemed almost perfect for solving these problems we had with Ringel circle problem. But are there more applications of this? So we saw that there are these other applications of this Gallows theorem with this method. Are there more additional applications of this restricted Gallows theorem, or maybe other restricted versions that you could apply with similar ideas? And in this line, it's worth asking what other variants you can get. So are there interesting variations from other than polynomial restrictions to other restrictions you can place on X? And another question is, if we use something looser or maybe entirely different to homothetic copy, so say if we allowed rotations as well, then can we get more out of a theorem like this? Like, can we get more restrictions on our set X if we allowed rotations, say? Okay, I'll stop there.